The next case that I'd like to consider is suppose you have a function of three variables, and each of those three variables is a function of one variable. The tree diagram in this case would look like the following. W is a function of three different variables, x, y, and z. And x, y, and z are all functions of one variable, that one variable being t. Now if I wanted to come up with an expression for the derivative of w with respect to t, dw over dt, this would be an ordinary derivative, not a partial derivative, due to the fact that we have only one independent variable in this case. So to get from w to t, we have three different ways we can do so. First one is to say go from w to x and x to t. So the first derivative will be a partial derivative, since w is a function of three of our intermediate variables, and then dx dt, because x is a function of only one variable. Or I can go from w to y and y to t, w to y and y to t, or I can go from w to z and z to t. This would be our expression, according to the chain rule, for the derivative of w with respect to t. Now to give you an example of one such case, I would like to consider the following. This time let's do w is equal to x squared plus y squared plus z squared, where x is going to be equal to the sine of t, y is going to be equal to the cosine of t, and z is equal to the tangent of t. This will help us get some practice with our trigonometric derivatives. So if I am going to go this route, then once again, dw dt is going to be equal to partial derivative of w with respect to x times dx dt, plus the partial derivative of w with respect to y times dy dt, plus the partial derivative of w with respect to z times dz dt. None of these derivatives is going to be particularly challenging, so let's finish them off. Partial of w with respect to x, we'll get a 2x from the first term. The other two terms will go to 0 because we're holding them constant. Times dx dt, that'll be the derivative of the sine of t with respect to t. Plus the partial derivative of w with respect to y, we'll get a 2y for that term. And then we'll also need a derivative of the cosine of t. That'll be the negative sine of t. Plus partial of w with respect to z, for the same reason as the previous two, we'll get 2z. And then multiply by dz dt. That'll be the derivative of the tangent of t. That'll be equal to the secant squared of t. Now there are some cutesy little trigonometric things that you can do if you wanted to perform substitutions on all of these. In fact, you know what? Let's go ahead and do it. Let's plug in what all of these parameterizations are. So this will be 2 times x, that'll be 2 times the sine of t, times the cosine of t, plus 2 times y, that'll be cosine of t, times the negative sine of t, plus 2 times z, z being the tangent of t, times the secant squared of t. Now actually you'll notice that these two terms that we got for our first two are actually like terms with opposite signs and will cancel each other out, leaving us with just 2 times the tangent of t times the secant squared of t. However, in celebration of the last problem, I wanted to show you what would happen if we decided to make substitutions first and then try to perform a derivative. So we'll say, or w is equal to x squared plus y squared plus z squared. Now hopefully any trigonometric student can tell you that when you see a sine of t quantity squared plus a cosine of t quantity squared, there is an identity for that, and that is equal to 1. We'd be differentiating 1 plus the tangent squared of t. So hopefully that justifies why these two terms wound up canceling each other out up here. It's because ultimately those two terms together were equal to 1. Now, even still, we could simplify this further by saying that 1 plus the tangent squared of t, that's another Pythagorean identity, and that would be the secant squared of t. So to differentiate w with respect to t is simply going to be a use of the power rule and the chain rule. We'll start with the derivative of something squared is 2 times that thing raised to the first power times the derivative of the secant. That'll be the secant of t times the tangent of t. You'll notice that when we try it this way, we wind up getting the exact same result as what we got before, just written in a slightly different order. So once again, there is some merit to making substitutions before differentiating, should you care to do so. You never know what's going to happen.